Asynchronous transfer mode is, according to the ATM Forum, a telecommunications concept defined by ANSI and ITU standards for carriage of a complete range of user traffic, including voice, data, and video signals. ATM was developed to meet the needs of the Broadband Integrated Services Digital Network, as defined in the late 1980s, and designed to unify telecommunication and computer networks. It was designed for a network that must handle both traditional high-throughput data traffic, and real-time, low-latency content such as voice and video. The reference model for ATM approximately maps to the three lowest layers of the ISO-OSI reference model: network layer, data link layer, and physical layer. ATM is a core protocol used over the SONET SDH backbone of the public switched telephone network and integrated services digital network, but its use is declining in favor of all IP. ATM provides functionality that is similar to both circuit switching and packet switching networks. ATM uses asynchronous time division multiplexing, and encodes data into small, fixed-sized packets called cells. This differs from approaches such as the Internet Protocol or Ethernet that use variable-sized packets and frames. ATM uses a connection-oriented model in which a virtual circuit must be established between two endpoints before the actual data exchange begins. These virtual circuits may be a Euro or a permanente Euro, that is dedicated connections that are usually pre-configured by the service provider, or a Euro-OI switch-keyed Euro, that is set up on a per-call basis using signaling and disconnected when the call is terminated. Layer 2 are Euro datagrams. In the ISO-OSI reference model data link layer, the basic transfer units are generically called frames. In ATM these frames are of a fixed length and specifically called cells. Cell size: if a speech signal is reduced to packets, and it is forced to share a link with bursty data traffic, then no matter how small the speech packets could be made, they would always encounter full-size data packets. Under normal queuing conditions the cells might experience maximum queuing delays. To avoid this issue, all ATM packets, or cells, are the same small size. In addition, the fixed cell structure means that ATM can be readily switched by hardware without the inherent delays introduced by software switched and routed frames. Thus, the designers of ATM utilized small data cells to reduce jitter in the multiplexing of data streams. Reduction of jitter is particularly important when carrying voice traffic, because the conversion of digitized voice into an analog audio signal is an inherently real-time process, and to do a good job, the decoder that does this needs an evenly spaced stream of data items. If the next data item is not available when it is needed, the codec has no choice but to produce silence or guess a Euro, and if the data is late, it is useless, because the time period when it should have been converted to a signal has already passed. At the time of the design of ATM, 155-bit synchronous digital hierarchy with 135-bit payload was considered a fast optical network link, and many polysynchronous digital hierarchy links in the digital network were considerably slower, ranging from 1.544 to 45-bit in the USA, and 2 to 34-bit in Europe. At this rate, a typical full-length 1500-byte data packet would take 77.42 a microsecond to transmit. In a lower speed link, such as a 1.544-bit ST1 line, a 1500-byte packet would take up to 7.8 milliseconds. A queuing delay induced by several such data packets might exceed the figure of 7.8 milliseconds several times over, in addition to any packet generation delay in the shorter speech packet. This was clearly unacceptable for speech traffic, which needs to have low jitter in the data stream being fed into the codec if it is to produce good quality sound. A packet voice system can produce this low jitter in a number of ways: have a playback buffer between the network and the codec, one large enough to tide the codec over almost all the jitter in the data. This allows smoothing out the jitter, but the delay introduced by passage through the buffer would require echo cancellers even in local networks. This was considered too expensive at the time. Also, it would have increased the delay across the channel, and conversation is difficult over high delay channels. Build a system that can inherently provide low jitter to traffic that needs it. operate on a one-one user basis. The design of ATM aimed for a low jitter network interface. However, cells were introduced in the design to provide short queuing delays while continuing to support datagram traffic. ATM broke up all packets, data, and voice streams into 48-byte chunks, adding a 5-byte routing header to each one so that they could be reassembled later. The choice of 48 bytes was political rather than technical. When the CCITT was standardizing ATM, parties from the United States wanted a 64-byte payload because this was felt to be a good compromise in larger payloads optimized for data transmission and shorter payloads optimized for real-time applications like voice. Parties from Europe wanted 32-byte payloads because the small size simplify voice applications with respect to echo cancellation. Most of the European parties eventually came around to the arguments made by the Americans, but France and a few others held out for a shorter cell length. With 32 bytes, France would have been able to implement an ATM-based voice network with calls from one end of France to the other requiring no echo cancellation. 48 bytes was chosen as a compromise between the two sides. 5-byte headers were chosen because it was thought that 10% of the payload was the maximum price to pay for routing information. ATM multiplexed these 53-byte cells instead of packets, which reduced worst-case cell contention jitter by a factor of almost 30, reducing the need for echo cancellers. The structure of an ATM cell. An ATM cell consists of a 5-byte header and a 48-byte payload. The payload size of 48 bytes was chosen as described above. ATM defines two different cell formats, UNI and NNI. Most ATM links use UNI cell format. GFC equals generic flow control, VPI equals virtual path identifier, VCI equals virtual channel identifier, PT equals payload type. CLP equals cell loss priority, HEC equals header error control. ATM uses the PT field to designate various special kinds of cells for operations, administration and management purposes, and to delineate packet boundaries in some ATM adaptation layers. Several ATM link protocols use the HEC field to drive a CRC-based framing algorithm, which allows locating the ATM cells with no overhead beyond what is otherwise needed for header protection. The 8-bit CRC is used to correct single-bit header errors and detect multi-bit header errors. When multi-bit header errors are detected, the current and subsequent cells are dropped until a cell with no header errors is found. A UNI cell reserves the GFC field for a local flow control submultiplexing system between users. This was intended to allow several terminals to share a single network connection, in the same way that two integrated services digital network phones can share a single basic rate ISDN connection. All 4 GFC bits must be 0 by default. The NNI cell format replicates the UNI format almost exactly, except that the 4-bit GFC field is reallocated to the VPI field, extending the VPI to 12 bits. Thus, a single NNI ATM interconnection is capable of addressing almost 212 VPs of up to almost 216 VCs each. Cells in practice, ATM supports different types of services via AALs. Standardized AALs include AAL1, AAL2, and AAL5, and the rarely used AAL3 and AAL4. AAL1 is used for constant bit rate services and circuit emulation. Synchronization is also maintained at AAL1. AAL2 through AAL4 are used for variable bit rate services, and AAL5 for data. Which AAL is in use for a given cell is not encoded in the cell. Instead, it is negotiated by or configured at the endpoints on a per virtual connection basis. Following the initial design of ATM, networks have become much faster. A 1500-byte full-size Ethernet frame takes only 1.2 microsecond to transmit on a 10-bit S network, reducing the need for small cells to reduce jitter due to contention. Some consider that this makes a case for replacing ATM with Ethernet in the network backbone. However, it should be noted that the increased link speeds by themselves do not alleviate jitter due to queuing. Additionally, the hardware for implementing the service adaptation for IP packets is expensive at very high speeds. Specifically, at speeds of OC3 and above, the cost of segmentation and reassembly hardware makes ATM less competitive for IP than packet over SONET. Because of its fixed 48-byte cell payload, ATM is not suitable as a data link layer directly underlying IP, since the OSI layer on which IP operates must provide a maximum transmission unit of at least 576 bytes. SAR performance limits mean that the fastest IP router ATM interfaces are STM16, STM64, which actually compares, while as of 2004 POS can operate at OC192 with higher speeds expected in the future. On slower or congested links, ATM DOS makes sense, and for this reason most asymmetric digital subscriber line systems use ATM as an intermediate layer between the physical link layer and a Layer 2 protocol like PPP or Ethernet. At these lower speeds, ATM provides a useful ability to carry multiple logical circuits on a single physical or virtual medium, although other techniques exist, such as multi-link PPP and Ethernet VLANs, which are optional in VDSL implementations. DSL can be used as an access method for an ATM network, allowing a DSL termination point in a telephone central office to connect to many Internet service providers across a wide area ATM network. In the United States, at least, this has allowed DSL providers to provide DSL access to the customers of many Internet service providers. Since one DSL termination point can support multiple ISPs, the economic feasibility of DSL is substantially improved. Why virtual circuits? ATM operates as a channel-based transport layer, using virtual circuits. This is encompassed in the concept of the virtual paths and virtual channels. Every ATM cell has an 8 or 12-bit virtual path identifier and 16-bit virtual channel identifier pair defined in its header. The VCI, together with the VPI, is used to identify the next destination of a cell as it passes through a series of ATM switches on its way to its destination. The length of the VPI varies according to whether the cell is sent on the user network interface, or if it is sent on the network interface. As these cells traverse an ATM network, switching takes place by changing the VPI-VCI values. Although the VPI-VCI values are not necessarily consistent from one end of the connection to the other, the concept of a circuit is consistent. ATM switches use the VPI-VCI fields to identify the virtual channel link of the next network that a cell needs to transit on its way to its final destination. The function of the VCI is similar to that of the data link connection identifier in frame relay and the logical channel number and logical channel group number in X25. Another advantage of the use of virtual circuits comes with the ability to use them as a multiplexing layer, allowing different services. The VPI is useful for reducing the switching table of some virtual circuits which have common paths. Using cells and virtual circuits for traffic engineering. Another key ATM concept involves the traffic contract. When an ATM circuit is set up, each switch on the circuit is informed of the traffic class of the connection. ATM traffic contracts form part of the mechanism by which quality of service is ensured. There are 4 basic types which each have a set of parameters describing the connection. CBR, constant bit rate, a peak cell rate is specified, which is constant. VBR, variable bit rate, an average or sustainable cell rate is specified, which can peak at a certain level, a PCR, for a maximum interval before being problematic. ABR, available bit rate, a minimum guaranteed rate is specified. UBR, unspecified bit rate, traffic is allocated to all remaining transmission capacity. VBR has real-time and non-real-time variants, and serves for bursty traffic. Non-real-time is sometimes abbreviated to VBR-NRT. Most traffic classes also introduced the concept of cell delay variation tolerance, which defines the clumping of cells in time. Traffic policing. To maintain network performance, networks may apply traffic policing to virtual circuits to limit them to their traffic contracts at the entry points to the network, that is the user or network interfaces and network-to-network interfaces, Usage Network Parameter Control. The reference model given by the ITU and ATM Forum for UPC and NPC is the generic cell rate algorithm, which is a version of the leaky bucket algorithm. CBR traffic will normally be policed to a PCO and CDVT alone, whereas VBR traffic will normally be policed using a dual leaky bucket controller to a PCO and CDVT and an SCR and maximum burst size. The MBS will normally be the packet size for the VBR VCN cells. If the traffic on a virtual circuit is exceeding its traffic contract, as determined by the GCRA, the network can either drop the cells or mark the cell loss priority bit. Basic policing works on a cell-by-cell basis, but this is suboptimal for encapsulated packet traffic. As a result, schemes such as partial packet discard and early packet discard have been created that will discard a whole series of cells until the next packet starts. This reduces the number of useless cells in the network, saving bandwidth for full packets. EPD and PPD work with the AL5 connections as they use the end-of-packet marker, the ATM user to ATM user indication bit in the payload type field of the header, which is set in the last cell of OSARSDU. Traffic shaping usually takes place in the network interface card in user equipment, and attempts to ensure that the cell flow on a VC will meet its traffic contract, that is, cells will not be dropped or reduced in priority at the UNI. Since the reference model given for traffic policing in the network is the GCRA, this algorithm is normally used for shaping as well, and single and dual leaky bucket implementations may be used as appropriate. Types of virtual circuits and paths. ATM can build virtual circuits and virtual paths either statically or dynamically. Static circuits or paths require that the circuit is composed of a series of segments, one for each pair of interfaces through which it passes. PVPs and PVCs, though conceptually simple, require significant effort in large networks. They also do not support the rerouting of service in the event of a failure. Dynamically built PVPs and PVCs, in contrast, are built by specifying the characteristics of the circuit and the two endpoints. Finally, ATM networks create and remove switched virtual circuits on demand when requested by an end piece of equipment. One application for SVCs is to carry individual telephone calls when a network of telephone switches are interconnected using ATM. SVCs were also used in attempts to replace local area networks with ATM. Virtual circuit routing. Most ATM networks supporting SPVPs, SPVCs, and SVCs use the private network node interface or the private network-to-network interface protocol. PNNI uses the same shortest path first algorithm used by OSPF and is to route IP packets to share topology information between switches and select a route through a network. PNNI also includes a very powerful summarization mechanism to allow construction of very large networks, as well as a call admission control algorithm which determines the availability of sufficient bandwidth on a proposed route through a network in order to satisfy the service requirements of a VC or VP. Call admission and connection establishment. A network must establish a connection before two parties can send cells to each other. In ATM this is called a virtual circuit. It can be a permanent virtual circuit, which is created administratively on the endpoints, or a switched virtual circuit, which is created as needed by the communicating parties. SVC creation is managed by signaling, in which the requesting party indicates the address of the receiving party, the type of service requested, and whatever traffic parameters may be applicable to the selected service. Call admission is then performed by the network to confirm that the requested resources are available and that a route exists for the connection. Reference model. ATM defines three layers: ATM Adaptation Layer, ATM Layer, roughly corresponding to the OSI Data Link Layer, Physical Layer, equivalent to the OSI Physical Layer, Deployment. ATM became popular with telephone companies and many computer makers in the 1990s. However, even by the end of the decade, the better price performance of Internet Protocol-based products was competing with ATM technology for integrating real-time and bursty network traffic. Companies such as 4 Systems focused on ATM products, while other large vendors such as Cisco Systems provided ATM as an option. After the burst of the dot-com bubble, some still predicted that ATM is going to dominate. However, in 2005 the ATM Forum, which had been the trade organization promoting the technology, merged with groups promoting other technologies, and eventually became the Broadband Forum. Wireless ATM or mobile ATM. While ATM is a great technology for high-speed networks, the wireless version of it takes the form of wireless ATM or mobile ATM. Basically, the core network is ATM while the access network is wireless. ATM cells are still being transmitted from base stations to mobile terminals. Mobility functions are performed at an ATM switch in the core network, known as crossover switch, which is similar to the MSC of GSM networks. The advantage of wireless ATM is its high bandwidth and high-speed handoffs done at Layer 2. In the early 1990s, Bell Labs and NEC Research Labs worked actively in this field. Andy Hopper from Cambridge University Computer Laboratory also worked in this area. There was a wireless ATM forum formed to standardize the technology behind wireless ATM networks. The forum was supported by several telecommunication companies, including NEC, Fujitsu, AT&T, etc. Mobile ATM aimed to provide high-speed multimedia communications technology, capable of delivering broadband mobile communications beyond that of GSM and WLANs. See also, VoATM, Notes. References, Black, Alice D. Atma Euro Volume 3, Internetworking with ATM. Toronto, Prentice Hall. ISBN A0-13-784182-5. Toprika, Martin. Asynchronous Transfer Mode. Solutions for Broadband ISDN. Prentice Haller, Joel, Amos E., Junior Asynchronous Transfer Mode. IEEE Presser, Galway, Tom. Planning and Managing ATM Network. New York, Manning. ISBN A978-0-13-262189-2. Magdisan, David E. Darren L. Spon. ATM Theory and Applications. Montreal, McGraw-Hill. ISBN A0-07-045346-2. Nielik Hunter, PSA Textbook on ATM Telecommunications, Principles and Implementation. CRC Press. ISBN A0-8493-1805-EXA, ATM Cell Format Cisco Systems, Asynchronous Transfer Mode, Cisco Systems, External Links, ATM Forum. Archived from the original on July 1, 2005. ATM Info and Resources, ATM Chip Web, Chip and NIC Database, a tutorial from Juniper website, ATM Tutorial.